So, good afternoon, guys. This is SYR, and now today we are going to see about a fundamental concept in terms of material testing, which is fracture. So, what is fracture? Fracture is basically the separation which is obtained in a solid body part when it goes through some amount of stress in the required amount of time. For example, if we take a piece of chalk and broke into two pieces, what we can obtain is the broken piece of chalk. The broken piece of chalk can be considered as the separated parts, and the joint piece can be termed as a solid body. The amount of stress we make on that part which really leads to the broken down of the piece of chalk. So, can this only be obtained in non-ferrous materials like chalk paste? No, it can also be obtained in ferrous bases and materials, etc. So, fracture is basically into two types. One is ductile fracture and the other is brittle fracture. Ductile fracture is basically known as the fracture which is basically obtained in a very small and significant amount of plastic deformations before getting failure, and the material under ductile fracture can extensively stretches and provides the signs of fracture. Okay, now we have already seen on ductile fracture, right guys? So next is ductile fracture can take up to several forms like single crystals. It can also be obtained in polycrystalline specimens. In case of single crystals of ductile fracture, it can only be obtained in HCP metals and may slip on successive basal planes, which is the planes which are constructed inside of a ductile material, until the crystal separates by the shear stress which is obtained in the material. But when it comes to the case of brittle fracture in the material can be observed by the quick rate of propagation with no space and time for the deformation, and a very little amount of micro deformation is observed. And it's also stated that brittle fractures can only be observed in BCC and HCP metals but not in face-centered cubic metals unless the material under brittle fracture goes through some factors which contributes to the grain boundary embrittlement, which is the major element for ductile fractures to have its slow and gradual amount of crack propagations. When polycrystalline specimens are stated, the examples are gold and lead. They can actually be drawn to a point before they get broken or before they get fractured. Okay, what is before getting broken? So if you look at this small piece of diagram, we can state that two separate pieces of a joint material can be observed over here. This is the model of cup and cone. The top part can be regarded as the cup and the lower part can be regarded as the cone. So under the amount of huge stress, these materials get broken into two parts, which is known as cup and cone. So we've been speaking about ductile, right? Why ductility is important in terms of materials in industries? The property of ductility is very much important because it is to indicate whether the metal which can undergo large amount of stress, temperature and work rate which especially the industries demand. A material which is rich in terms of ductility indicates that the material has a property to deform locally without getting fractured. As the point of likely to deform locally is about local deformation. What is local deformation? Local deformation is basically the property of the material to get deformed inside of itself without getting affected by any external factors. If we look into brittle materials, it can also fracture almost to the elastic limit. elastic limit of, when you observe in this graph, the stress strain curve of a completely brittle graph is almost like a straight line. But if you add slighter amount of ductility in the brittle material, we can observe a small curve, a small upward curve over here, which clearly determines the presence of ductility as well as the yield point over here. And the plastic deformation gets moved on throughout this. Okay. However, with brittle materials, localized stress continues. The localized stress which you can observe inside of the material continues to build on because there is no local yielding inside of the brittle materials. Okay, we stated about previously stresses, but what if these materials are impacted under the temperature? The ductile material cannot be transformed into brittle material. No, both these materials can transform into either, but under selective temperature and selective conditions. For example, a metal like tungsten, which is naturally at room temperature, can be converted into a ductile material at a rise in temperature or an elevated temperature. And another property here states that a metal which is brittle in nature may be converted to ductile under hydrostatic compression. Furthermore, a metal which is ductile in tension at room temperature can become brittle in the presence of notches. In the presence and pressure of notches and low amount of temperatures and high rates of loading, which is especially the work rate, are adding up of embrittling agents such as hydrogen. Okay, we have clearly seen about the overview of ductile fractures. Now we go into characteristics of ductile fracture. Okay, clearly ductile fracture have a property of plastic deformation in a very large amount, because the material which is under ductile fracture undergoes a process of elongation in an extended amount of time, which really leads into the propagation of cracks in a slow and a gradual manner, which can lead to high energy absorption of the material. The material has the capability of absorbing substantial energy during the deformation process by the cracks which are formed internally over it. Next, the next stage, as a material moves on through it, necking is happening. Necking is basically the property where before the material gets fractured. Okay. Stages of ductile fracture. Stages of ductile fracture where the void can be observed in a nucleation manner. The voids which can only be obtained at the beginning in a small cavity size of amount. The small cavities are formed at the grain boundaries inside of the material, which can also be termed as impurities, inclusions during the process of plastic deformation. As these cavities moving on to grow towards it, the void growth is observed over there. The voids gradually increase in their size as the material which continues to get deformed plastically. Then those cavities become larger and closer together, which forms the property of void closings. Here the voids join together, forming a crack which propagates rapidly and causes a final fracture of the material. Okay. Previously stated about the cup and cone fracture pattern. This is a typical ductile pattern which can observe in any ductile material, which is on the left side we look into a depression sized shaped cup, and the opposite side of this fracture pattern can be observed in a cone way, which is a protrusion. This cup and cone basically indicates the ductile failure mechanism. Okay. As we previously stated about the stress strain, right? The material under ductile fracture passes through its elastic region and obtains an yield point, and then goes on through a plastic deformation, then obtains a state of necking and finally gets fractured. Here we can get an examples of copper wire stretching and breaking due to high and low amounts of temperature pressures, and aluminum deformation. Next, we look into a slightly another one is as essential as ductile fracture, which is brittle fracture basically. Brittle fracture has no amount of plastic deformation, unlike ductile fracture which undergoes plastic deformation. They have a fast crack propagation unlike ductile fracture propagation. Then the sudden in crack propagation forms a smooth surface of the fracture, which really forms a flat surfaces, and this can also lead to low energy absorption of the brittle materials. Next, if we compare those ductile and brittle fractures, we can observe characteristics of deformation, crack speed, energy, surface, etc. Okay. In terms of deformation, ductile fracture have a very large amount of plastic deformation, and otherwise the brittle fracture have little to no amount of deformation. But in the crack speed, it is very contrasting in ductile fracture as it is very slow and gradual amount of propagation of cracks. But in terms of brittle materials, it undergoes through a fast, quick propagation of cracks. This really results in their energy absorptions, as the ductile materials, which is slow and gradual amount of propagation of cracks, can really absorb high amount of energy, but the brittle have a very low absorption energy. This can lead to those surfaces which is ductile have a rough and fibrous surface, but brittle fracture have a smooth and flat surface. Then we previously stated about the presence of temperature or the property of temperature in the transitions of ductile and brittle, right? The temperature which the property change of ductile to brittle is known as ductile brittle transition temperature. So what is basically dBdt? dBdt is a temperature below which a material can change from ductile behavior to brittle behavior. It is very common in BCC materials like ferritic steels, and which is very important for low temperature applications like cryogenic engine, and it is also used in Charpy impact test. So what is important? Why dBdt is important in terms of industrial purposes? Because dBdt measure can really prevent sudden brittle fractures which is observed in materials. It ensures a clear, safe environment during colder times, and it helps in selecting suitable materials which can undergo the process of low temperature and high pressure. It really reduces risks of catastrophic failure, which observed in our upcoming example. The example is Titanic ship. So we all know the Titanic ship is a very famous one which got sank and which got hit an iceberg and got sank into two parts. Basically, Titanic ship has been constructed with the property of a ductile aluminum. But when the Titanic ship passes through the region, Arctic regions, under the amounts of lower temperature, dBdt process started, and then the ductile property of the Titanic ship got converted into brittle, and when the brittled material of that ship got cracked with the iceberg, it really results in the breakdown of Titanic ship, which really caused a catastrophic failure. Okay. We stated about cryogenic steels, right? So as we move on to the cryogenic storage tanks, which has a storage of LNG of minus 162 degrees centigrades. It can also be used as cryogenic pressure vessels, and for those cryogenic pressure vessels, austenitic stainless steel is preferred because the material of austenitic stainless steel is completely ductile and it cannot become brittle. So I hope that you guys have got a clear understanding of how fracture works, and especially ductile and brittle fracture work, especially ductile fracture works. So thank you all. Please kindly like, share and subscribe. Thank you.